Pleasant afternoon, everyone. For my Chem 15 students. So this afternoon, we are going to discuss about this is chapter 6, about molecules and materials. This will be the last topic for finals. So we'll have 3 topics for finals, that is chemical bonding, energy and matter, and molecules and materials. That other 2 that is still incoming, about nuclear chemistry, and the other one will be unassigned readings or assigned video. I will still have a video of that. So this topic is about molecules and materials. These are the different objectives. Okay. We have a quite long objective for this molecules and materials, especially this will pertain, we are going to touch about different bonds. Okay, the bonds is the one that connect between an atom with another atom, a molecule with another molecule, or to form into a compound. Okay, so the first thing that we are going to discuss here is about carbon. So carbon has 3. We will find it out that it has 3 types. Okay, that is the graphite, the diamond, and we are going to compare its properties and its structure. We will also discuss about the arrangement of the atoms. There are 3 arrangement of an atom, and we will also look into its efficiency, its packing efficiency. We will also describe what is bond theory, especially in solids. We are going to differentiate metals, insulators, and semiconductors, and we will look into its types and its classification. Of course, we will also describe some properties of materials, and let us differentiate these properties with metals, insulators, and semiconductors. We will identify the different types of IMF, that is the intermolecular forces, as I have said, the bonds. We will also explain the connections of that IMF. IMF is short for intermolecular forces, and its properties with the boiling point and vapor pressure. We will also look into the application, especially in polymers, and also describe what are the properties of these polymers in a molecular structure. Okay, let us start with this topic with carbon. What is carbon, by the way? Of course, as you can see in the periodic table, this is a non-metal. Carbon is a non-metal with, it has number 8, atomic number, and a 6, then it has a molecular mass or molecular weight of 12 grams per mole. That is carbon. But there are 3 forms of carbon. That is graphite, diamond, and the latest one, this graphite and diamond is already been known a long time. Then fullerenes, that's fullerenes. Fullerenes is the latest. Okay, so graphite and diamond is the old discovery of forms of carbon, and fullerenes was discovered way back earlier, 1985, in a form C60, meaning how many carbons? 60 carbons, which is linked together. Okay, so C60 was named after Buckminster Fulleren. He named it because it resembles the doom. The doom popularized. This doom is popularized by an architect, Buckminster. I hope you know about this because you are an engineering student. So carbon has many uses. Its material has many applications. One of this, Of course, diamond. Diamond is one of the form of carbon. No? It is being used in the jewelry. Diamonds are stone. Okay. Diamonds, di ba? There is a song, Diamonds Are Forever. Ano man, particular ang mahala ng diamonds. Okay. It's a stone. Huh? Unlike with graphite, diamonds are very strong. That is why it needs a diamond to cut a diamond. Yeah, that's it. Because in the diamond, what is very important is its size, its clarity. Yeah, the more bigger the diamond and more clear and more, it will give more brilliant sparkle. It will be more expensive. Okay. While graphite is the counterpart of a diamond, which is barato. The one which is used in the lead pencil is a graphite. So graphite is used in the pencil. It is also used as lubricants. Lubricants is in the diesel. Have you seen it? Okay. It is in a color of black. Yeah, that is why lead in the pencil is black. And also it will be used as composite material. For fulleriness, until now, it is still looking into its uses in the nanotubes, and still on the process of exploration because this is a new technology. So those are the three forms of carbon, the graphite, the diamond, and the fullerene. Okay, so let us look into the temperature at the same time. The temperature at the same time, the pressure. Actually, as you can see here in this graph, so this graph here is known as the phase change, phase diagram. What do you mean by phase? Meaning, as you look into this is a comparison between diamond and graphite. Take a look. The temperature here is 1,000 down under the graph. 1,000, 2,000, 3,000. And the upper portion, the x-axis is the temperature, the y-axis is the pressure. The graphite has a pressure of 200 and the maximum of 400. No? So this is in between graphite. Graphite could have, you can heat it until 3,000 degrees Kelvin. Okay, but in diamond, it's different. Okay, the diamond here, as you look into it, it has a higher temperature in order to change that into its phase. So this is in a form of solid, this one, solid. It will rise up here in a form of liquid. Pero dito sila kaabot anak tayo. No? So as it changes, what happened? No? So graphite will only up to the pressure of 200. Beyond that is it in the form of diamond. So graphite has a lower temperature compared with diamond, lower pressure also compared with diamond. So this is the phase diagram showing in which state of the phase compound will be stable. So it will be stable, graphite will be stable at this portion here, while diamond will be stable at this portion here. That is almost 400, 400 atmospheric pressure and 3,000 for the temperature. Here, gamay pa ang temperature, dili ka taas at zero. The temperature, it's already, the pressure is, it needs a greater pressure for diamond to change into diamond from this portion here. Paubos ang yung pressure. So, actually, if you are going to manipulate by changing the temperature and pressure of a compound, you can change its state or phase. That is in the phase diagram. Okay, so carbon in a form of fullerene, it is used in nanotubes. These are nanotubes. Nanotube. Nanotube compared with the plastic, the PVC tubes. Nanotube is much, much stronger because this nanotube has a high tensile strength and higher than steel. The Asian tensile strength meaning it could not easily be broken up. It's almost unbreakable if it is in a form of nanotube. So nanotube growth with metallic element, this will have a promising, promising industry. In the nanotube, what is being in place there are wires. So this is one of the uses of the carbon in a form of fullerene. Fullerene. So in the condensed phase, especially in a solid, so atoms or molecules has two forms, solid form. That is the crystalline solid and the amorphous solid. If you talk about what's the difference between crystalline and amorphous, in the crystalline solid, it has a regular repeating geometric arrangement of the atoms or molecules. Regular repeating geometric arrangement of the atoms. Same thing in an example of this in the ice in a form of solid. It has a repeating geometric arrangement. The amorphous solid, this kind of solid has what is its arrangement of the atom? It has a random arrangement. So to distinguish between crystalline and amorphous, crystalline has a regular repeating geometric arrangement, while amorphous has a random arrangement of the atoms or molecules. Its packing efficiency. What is the difference between the packing efficiency? But before that, what is packing efficiency? So packing efficiency is the percentage. Now this is the crystalline solid. This pertains about the percentage space occupied by the arrangement, meaning how close or how packed or how closer the knit between the atoms of or the molecules. The farther it is, what do you think will happen? Okay, more empty space. But if it is closer, halos wala siya empty space. Take a look. So the less empty space in packing of atom molecules in solid, the higher the packing efficiency. Kung less ang empty space, taas iyang packing efficiency. But if there are more empty space, of course, lower iyang packing efficiency. So the higher the packing efficiency, the higher the density of the solid, and at the same time, that solid is stronger compared with a lower packing efficiency. Let us take a look into this example. An example are marbles or julin. These are marbles here, which is being arranged in two different manner. This is the first one. As you can see, there are empty space in between one marble to another marble. Okay, so there are large gaps. If you talk about this space, the other term used there are gaps. There are large gaps with the rows lined up. So this is that row there. Mga row nga na. Pero in between row, there are empty space. Okay, large gaps or there are gaps. If you look into this second, in B, smaller gaps with the rows affect with one another. So here, there are smaller gaps. So looking into this, which do you think will have a higher packing efficiency? Of course, this one, this closer knit or less gaps compared with this. This one will have a lower packing efficiency. So these are marbles. This is our model. The large gap between a line, this A, indicates lower packing efficiency. And what is its packing efficiency is 76%. While this B has a smaller gaps between offset rows, indicates higher efficiency, about 91%. So, how are we going to maximize packing efficiency? There are three ways in lessening the packing efficiency in order to have a greater packing efficiency. So the first one is, of course, that is the first layer. First layer na siya. Ang buhaton kuno is the second layer of the atoms will stack offset the first layer of atoms. Meaning it should be, it's not on in line. More pareha ba sa marble, kinalan in place. Okay. This will give about 74% packing efficiency. Meaning, the importance here is looking into the next layer. So the next layer will determine its packing efficiency. Then the third layer can stack directly above the atoms. Take a look. This is the first layer. So you pack now the second layer. This is the second layer. First layer, second layer. So pag butang nimo, it should offset. It should offset the first layer, meaning the empty space in the first layer should offset, meaning tabunan to nimo tong mga gaps. Okay. So the third layer should directly stack above the atoms, and that is the atoms in the first layer. So what kind of packing is that? That is hexagonal close packing, HCP. And the third layer can stack directly above the hollow in the first layer. So katong sa third layer nga mo stack siya sa first layer, unsa to siya? That is the HCP. That is the hexagonal close packing. And the third layer nga mo stack above it is known as cubic close packing, the CCP. Okay, so let us look into the different structure of the crystal. But before that, let us define what is unit cell. Okay. So a unit cell, by the way, is a unit cell is the smallest collection of atoms that display all the features of the crystal structure. So that is unit cell. Katong kada gamay nga atom that will display ang structure sa crystal is known as the unit cell. There are three crystal structures that display this unit cell. The first one is the SC. This is now the simple cubic here. This is the simple cubic. That's the first crystal structure. In the simple cubic, how many corners? There are 8 corners. Take a look. That is 1, 2, 3, 4, 5, 6, 7, 8. There are 8 corners in the simple cubic. Okay. 8 atoms in each corner. While the second one, this picture here, is the BCC. The SC, then followed by the BCC, that is the body-centered cubic, BCC. It contains same time 8, but at the center, it has an additional of 1. So 8 plus 1 is 9. Okay. And the last type of a crystal structure is the FCC, the face-centered cubic. Okay. It has 8, then after 8, gitabunan pa siya sa additional nga 6 here. Take a look. So, naay to nga ni ang body-centered nga usa, ang nga ni sa face-centered cubic na ay unum in between, tabon or gi-alternate sa gaps between this the phase cubic centered. So 8 tapos na pag 6. Okay. So how are we going to calculate the efficiency, packing efficiency? It will differ with each unit cell. So for the face-centered cubic, this is the formula. That is 1/2 multiplied by the face of the center atoms plus 1/8 multiplied by the number of cornerstones. So there will be 4. Then we have the body-centered cubic. That is the number of body-centered atoms plus 1/8 multiplied by the corner atoms, which has 2. And the last one is the simple cubic. That is 1/8 and the cornerstone, which is equivalent to 1. So how are we going to find its volume of the atoms occupied by this? So the volume could be computed by looking into the number, the radius of the diameter or the radius of your structure. So the total volume occupied by atoms is equal to the number atoms in unit cell multiplied by 4/3 pi r cubed. What is this 4/3 pi r cubed? Because they are in spherical form. Diba? The spherical form has a formula of 4/3 pi r cubed. Okay, so how are we going to calculate now the volume in each of the unit cell with the 3 structure? Okay, the volume is equal to, diba? If it is in a form of cube, that is a volume is a cube. This A is the edge length of the unit cell. But you will have different computation for the edge. That is why the volume of unit cell will differ in these 3 forms: the SC, the BCC, the FCC. Okay, so for the edge for the face cubic centered, you will have a formula 2 multiplied by the square root of 2 multiplied by r. That is for the edge for the face cubic centered. For the body centered cubic, you will have 4 divided by the square root of 3 multiplied by r. And the simple cubic, you will have an edge equal to 2r. So this is it. So this will be how are we, if we are going to solve now with our edge, the edge length, just have that into the volume, this formula volume here, you will get now the volume of your structure. Okay, so how are we going to solve for the packing efficiency? Packing efficiency is equal to the volume of atoms in unit cell over the total volume of atoms in an unit cell times 100. Okay, that's the packing efficiency. Now, we will have problems later about this. But let us look into the different, actually in this chapter, what we are going to do is these are more definition, these are more explanations about, because this is about materials, okay? The next thing is what is meant by coordination number. The coordination number is the number of atoms immediately adjacent at any given atom. No? So it will have, because we have 3 crystal structure, it will have different coordination number. For the SC, what will be the coordination number? Remember, it is equal to 6. For the BCC, the body-centered cubic, what is the coordination number? It's 8. And the closed pack, that is the FCC, it has coordination number of 12. That is coordination number. So, what's the connectivity of coordination number? How about if it will increase or decrease? Okay, so as coordination number increase, what will happen to the atom in its structure? The lattice interacts with more neighbor atoms. So, kung i-increase mo ang coordination number, the more an interaction sa atoms with its neighbor atoms. Another thing is the attractive force of this interaction hold the crystal together. So the more you increase the coordination number, the more there will be interaction with the neighboring atoms, the more there will be attractive force. And what will happen? This will make your crystal together more stronger because of this interaction. For the closed pack structure, no, because it has a coordination number of 12, this has having more common crystal structure. Mas dagan ang crystal structure with the FCC compared with the BCC and the SC. So looking into this, okay, the color here, looking into the different elements, makita ninyo unsa siya ang crystal structure niya. Na? So this brown ba ni siya? Na? Unsa siya? That is the simple cubic, the mercury, the bismuth, polonium, oxygen, fluorine, the actinium, and antimony. They are simple cubic. How about for the BCC? What's this? It's that I could not look into much its color. More light blue. Okay. This one is light blue. Okay. The calcium, the strontium, like that. Then the face centered, that is the darker blue. Okay. So on and so forth. So these are the color of the type of the crystals in its form in the different elements. So the properties of solid is interrelated with the structure of the crystal. In what way? So each carbon atom in the diamond is covalently bonded to 4 neighboring atoms. So diamond, so in diamond, what happened? It is bonded to 4 neighboring atoms. Mao di ay nga ang diamond is a very hard metal. Why? Because it is covalently bonded to 4 neighboring atoms. How about in graphite? So we will explain now the crystal structure with the properties. What makes this carbon in a form of diamond, in a form of graphite, much stronger or not so strong? Nga naman, So first reason is in diamond, what happened? It is covalently bonded to 4 neighboring atoms. That makes diamond hard. How about for graphite? Covalently bonded gapon siya, but not in 4 neighboring atoms, but covalently bonded into flat sheet. That is why, flat sheet siya, flat sheet. That is why graphite could easily slide with each other. Okay, flat sheet man siya, flat sheet. And graphite is not really that strong compared with diamonds. So this is now the form of the carbon joined together by diamonds. It is in a tetrahedral geometry, kaning ani. So it's difficult to break. It's difficult to break the bond between this. Unlike with this flat sheet, flat sheet na siya. This is in graphite. They are held together by weaker forces. These are covalently bonded with how many? 4 neighboring atoms. Upat. 1, 2, 3, 4. Tapos 1, 2, 3, 4. So maunang lisod siya i-break. It has the large number of covalent bonds in diamond explains its high strength of diamond. Okay? So let us look into metals, insulators, and semiconductors. Let us define this by means of its properties. First is the bonding metals. No? So for metals, what are its properties? This is very common when you are still in senior high or in your junior high. You already know the properties or the characteristic of a metal. Metal, it is shiny. Metal is ductile. Metal is malleable. Metal are good conductors of heat and electricity. Of course, you know that. Okay, so if you talk about malleable, meaning you can have that into sheet. That is why metals could be made into foils. Diba? Foils. Okay. Foil. Not yung mga silicone foils. Okay. Aluminum foil like that. No? So they are ductile. Ductile in a way that metals could be formed into sheets or into wires. Diba? Kanang scene, pwede na ito na siya maana, ma-fold, ma-circle. Why? Because it's malleable. Kanang metal in a form of copper wire, you can have that into coil. Why? Because they are ductile. That is properties of metals. So bonding in metals cannot be explained in terms of ionic or covalent. Di mo siya mabalaan. Ngano nag-bond ba na siya? Yeah, because it is known as metallic bonding. No? You already know that there is ionic bond, there is covalent bond. No? Okay. Pero na metallic bond. No? Metallic bond cannot be explained by means of the sharing of electrons or no, the sharing of electrons or the transfer of electrons, because by itself it could form into a metal sheets, no? By means of metallic bonding. No? What happened no? Here is, if you look into elements, no, there is little electronegativity. That is why they could not form into ionic bonds. Then their outermost subshell are not filled if you have that into bonding with metal with another metal. So what happened here? Once a metal combines with another metal, it does not need the octet rule. Can you still remember the octet rule? Meaning, when sodium reacts with chlorine, it gives off one electron to chlorine because chlorine needs to be 8, like that. But in the metallic bonding, wala na siya. No sharing and no transfer of electrons. What we have here in the metallic bonding is known as the sea of electron model. Sea of electrons model. No, sea of electrons, meaning puro ni siya metals. Puro ni aluminum, puro ni siya aluminum. No? So the sea of electron model is the first and simplest qualitative explanation of metallic bond. Nganong pwede ba nato siya mabind? No? Copper with copper like that? Oh, yeah. Nga naman, because of the metallic bonding, which is known as the C electron model. What happened here is the valence electrons are delocalized and move freely throughout the solid. That is why these metals could combine together. This explains also, no? Ang mga electrons nila pwede localized, meaning pwede mo transfer to the other one. Ano man? Because they could move freely throughout the solid. So this explains its properties of malleability, ductility, conductivity of the metals. Take a look here. No? So, di ba may metal, all of that has positive charge, walay negative. No? Okay, positive. For instance, this is your sea of electrons, no? In a metal. Kung imo kayo na siyang i-hammer nga na, imo na siyang, if you will, if you are going to no, have a force here by pumping it with a hammer, what will happen? Matingalan ka basta metal, magupi. Oh yeah. Why? That is what is meant by, no? It could easily be deformed. Nga naman, kani-ngani diba? The electrons could delocalize and they could move freely throughout the solid. That is its properties. So, mo nang, no, what will happen? Mo nang ma-deform siya. Nga naman. Yes, because if a force is applied to the metal, what will happen? This will coincide. If you pound it harder, of course, the stress, it is related to the stress and the strain. No? The more mo siya iduk-duk, the more po siya ma-flatten. Diba? Okay. So why? The free flow of electrons maintains the bonding throughout the process. That is why it could be flattened. Na? Nga naman, because the sea of electrons will just move. Freely move and be delocalized. No? So that is in the metallic bonding of metals. Okay. What do you mean by bond theory? Bond theory has something to do, this is the quantitative. If you talk about quantitative, it is the measure. Quantitative, it will always give you that answer of how much. Okay, that's quantitative. Now, it's a quantitative model of bonding solid. Okay, that's the bond theory. Okay, so the bond theory could have these different functions. The wave function, which is the valence electron interact with each other. That's the wave function. So in the bond theory, there are two forms. If you are going to hammer it and it will have a constructive interference, meaning ma-deform, what kind of bond theory is that? That is bonding molecular orbitals. Ingani kag bonding molecular orbitals, this will result to constructive interference. Okay ra, no? Ma-flatten lang, dili madaot. Okay. What happens if and when there is a destructive interference? That is known as the anti-bonding molecular orbital. The one which will result to constructive interference is bonding molecular orbitals. The one that will result to destructive interference is anti-bonding molecular orbitals. As you look into this, diba, mostly in this topic are all definition of terms. Yes, cannot share. That is why this has something to do with the materials. This will explain how metals, non-metals, behaves. Okay. Many more. So the number of molecular orbitals formed equal to the number of atomic orbitals involved. So in every bonding molecular orbital form, nagyo po siya one bonding molecular orbital that is formed. For what is bonding molecular? Constructive interference, naa po ang result. Kung naay constructive interference, naagyod po siya counter. There is always a counter bonding which is known as the anti-bonding molecular orbitals that will be formed from the constructive to destructive. Okay. So for odd numbers of bonding atoms and non-bonding molecular orbitals also is being formed. So the molecular orbitals formed belong to the entire set of atoms. It could either be for bonding molecular or the anti-molecular bonding orbitals. How about its energy? There are two types of energy encountered by metallic bonding. The first one is the bonding molecular orbitals. If it is bonding molecular, diba, it is this bonding molecular orbitals has something to do with constructive interference. But what happened to, kung constructive interference, what happened to its energy? It will be lower. But if it is a destructive here, na, interference for the anti-bonding, what happened? Your energy will be higher. Opposite ni siya, ha? Na, sa bonding molecular, lower ang energy niya, na, ano man, na, constructive interference, like constructive. For destructive interference, it will have a higher energy. No? So, this is the models of metallic bonding with its energy. No? So, as the number of atoms increases, the numbers of bonding and anti-bonding molecular orbital also increase. Kung tungagan mo ang atoms, what will happen? Dungag po ang bonding of anti-bonding molecular orbitals. No? So the energy, how about the energy? No? The energy spacing between molecular orbital decreases. Opposite, ha? Kung i-increase nimo ang number of atoms, mo decrease ang iyang energy spacing. No? And what will happen? Large number of atoms, the energy level merge to form continuous bond allowed energy. So, increase ang number of atoms, no, will decrease the energy spacing. It will have a large number of atoms in between energy level. Okay, that is in the metallic bonding. For the bond theory, what do you mean by bond theory? So the bond theory has something to do with the addition. At the same time, the kind of an atom wherein it will counteract or it will combine. Okay, that is the bond theory and conductivity. So looking into its principle, electrons feel the lowest energy band first. Diba? Unahong magkatong kadumdum mo itong SPDF. Okay, okay. The electronic configuration, unahon ang lower level energy, no, before mo filled up sa higher energy level. No? So that is electrons feel the lowest energy band first. Okay. So the energy difference between filled empty bonds determines its electrical properties of the bulk materials. So, no, the band populated by valence electrons is called the valence band. Katong madungag electron, no, that will be known added into the valence band. No? Katong, no, empty band above valence band is known as the conditioned band. No? Then, the energy difference between valence and conduction band is known as the band gap. So, we are talking about here definition of terms. Ala, daghan yun mo. No? Daghan definition of terms here. Daghan mo memorize on. Okay. So, let us look into the current flow. No? Current flows when electron moves from the valence band to the conduction band. So what happened? No? Let us look into the different forms. No? So kung the current flow will move into the electron, no, from valence band to conduction band, what will happen to materials which are conductors? What will happen to materials which are insulators? What will happen to materials which are semiconductors? So, mag-move ganyang current flow sa electron, no? What will happen to the conductors? They will have small bond gaps, meaning dugol. Madugol na noon sila, no? So a very small amount of energy is required to move electrons to the conduction band. So that is for conductors. So there will be small band gaps. How about for insulators? There will be large band gaps. Nga naman, a large amount of energy is required to move electrons to conduction band. How about semiconductors? No? The semiconductors is in between. Diba? in between metal and non-metal. No? That is why they are so-called metalloids. No? Have band gap intermediate. So na siya tunga-tunga. Dili siya dako, di po siya gamay ang band gap niya. No? So it is in between. Gap intermediate. No? There will be a gap intermediate. So here in this diagram, you can see this is the metals, this is the semiconductors, this is the insulators. The metals has a very, halos walay gap. No? But semiconductors tanawa, the band gap medyo taas-taas. Ang pinakataas are the insulators. No? So the band gap will be, in the band gap, there will be less band gap in metals, followed by the semiconductors, and the last is insulators. Ang pinakadako og band gap is insulators, followed by semiconductors and the metals. So that is the band gap diagram for conductors, semiconductors, and insulators. Okay, take a look. Kung dako gani ang band gap, what will happen? Ang conduction nimo og ang valence band, no? Ang conduction sa metal, conduction band o valence band almost equal. And the semiconductor, no? Equal gyapon siya. Pero gamas gamay ang iyang conduction band compare nimo sa metal. Kaya nga naman namin siya band gap, no? But for insulators, no, dako kaayo ang iyang band gap, no? Mas, no, ang conduction band layo kaayo siya sa valence band. Okay? That's it. Let us define now. So we are finished with metals. How about the semiconductors? We are finished with the conductors. So what are semiconductors? They are electrical conductivity of semiconductors. They could be described by means of doping. What's doping? Doping is adding trace amounts of element into a substance to modify its properties. You're going to add on, na aron mautron nimo ang iyang properties. There are two ways of doping. The N-type doping and the P-type doping. Okay, how it is being prepared. And the N-type doping, what is being doped? What is being added? Prepared by doping with valence electron-rich element. Itong mga negative element, negative charged element. Mo i-add nimo sa N-type. For the P-type, unsa man? So, it is prepared by doping with valence electron with deficient element, meaning the positive. The cation, this is the anion. Okay? That is the difference between the N and the P-type. N-type, it's negative. Why? Because you dope or add it. Doping with valence electron-rich element. The P-type, you add or dope this with valence electron deficient element. That's the difference between N and the P-type. That for semiconductors. More of this, the N-type semiconductors, let us differentiate between these two. They have extra valence electrons that fills donor level, which is just below the conduction band. They have little energy needed to promote the donor level of electron. The P-type semiconductors, here, the difference here in the N-type from the P, the N-type, they have extra valence electron. The P-type, they have lack of valence electron. In the N-type, they fill the donor level. Here, they create the acceptor level. That's it. Then, they have the same little energy, pero kani to promote the donor level, kani to promote the valence band electron to acceptor level. Kanito donor level. No? So, always remember that the vacancies in the valence band are holes. Okay. Katong na mga bakante, no, nga valence band, they are known as holes. Okay. Looking into this is the N-type pa ni siya. Take a look in the N-type. No? So to donor bigyan na promote sa N-type. No? So here, the donor electrons are promoted easily into conduction band. This is the conduction band. This is the valence band. Ha? Only ang conduction band. This is the valence band. Unsa tong sa N-type, they are promoted to the conduction band. Okay. So, doping with phosphorus, kana i-add on na nato siya phosphorus, introduce extra valence electron. No? So, what happened? Extra electron fills the donor level na anangan which lies closer to the conduction. Kani. Mo ni ang mga phosphorus, which will lie close to the conduction band. This is the conduction band. How about, okay, how about the P-type? Bali ang P-type, mo add to siya sa valence band. Na? So, as acceptor, so what happened if you add here, dupe with silicon, ganina, gidupe dato og phosphorus ni, dupe silicon, we add here, silicon, we add it here, what happened? Hing sa donor level, hing transfer siya into the conduction band. Kani, hing transfer siya sa valence band. Okay? So, aluminum is the most common type of P-type dopant. Okay? So, this will be your assignment. Okay? Let's have the junction. What do you mean by junction? Asa the pita, naa siya mga in-between. Okay? P-N junction can be constructed from P-type and the N-type. So the flow of electron across junction is easily regulated by applying voltage. So this is very important. Even in our houses, na mga junction box. Okay. So that junction is needed in order to regulate the voltage which is being applied. That's it. Important also in solid state electronics. Okay, so this is the PN junction. Simply switch when the correct voltage polarity is applied. Pag switch nimo, from positive to negative, it will flow into the next junction. Okay. What are the different bonds or what are the different forces in this metallic bond? Okay, metallic or for metals, for conductors, semiconductors, and insulators. Okay, the first thing that we are going to discuss is the IMF, that is the intermolecular force. The IMF has two forces. It could either have the attractive and the repulsive forces between metals. That is IMF. Attractive and repulsive IMF forces are weak comparison to bonding forces. Weakness siya compared with the bonding forces. Bonding forces is the covalent and the ionic bond. Okay. So the IM forces are largely responsible for determining the properties of the condensed phase, especially in solid. So the principle of minimization energy applies here well. Minimize niya ang electron flow. The next one, that is the IMF. Sunod is the dispersion force. What is meant by dispersion force? The common term used for dispersion force is London forces. Okay. Also, these are referred as instantaneous dipole-induced dipole forces. Here, what happened here? There are two oppositely charged points separated by some distance. So two oppositely charged, positive, negative, which are separated by distance. And that is known as the dipole or London force or dispersion. No? Separated. Dispersed, gani kay medyo naa siya space. Okay? So in dispersion, no, the instantaneous dipole occurs when fluctuation in electrons density for an atom or molecule is produced. Kung naay mag-fluctuate, hinay, magkadakhan, magkagamay, magkadagtuo, no, ang electron flow, what will happen? That is what is meant by instantaneous dipole. No? So instantaneous dipole are short-lived. Dili yung kaini siya strong, di ba? No? Unlike with the bonding forces. No? It's not that strong. The other one, ang una is induced. When kang induced occurs when fluctuation in electron density of an atom or molecule produces a dipole. The other one is induced. No? Induced dipole is created when an external electrical field forces a dipole to exist. No? Under it is a permanent dipole. Under instantaneous dipole is, no, this is the formation and disappearing, no, of electron flow. It is short-lived. Okay. So this is a dispersion. Take a look. Dako din siya space in between. No? That is why it's so-called dispersion, because there is, no, there is a space in between two atoms. No? So the external field, the electrical field distorts the electron density around the atom or dipole, inducing a dipole. Okay. So in dispersion, no, they are weak. Why they are weak? Because the sum of dispersion force over Avogadro's number of atoms are significant, no? Results in significant amount of energy. No? The next one is dispersion force holds many liquids together, solid and liquid together. That makes them weak. Okay. So the strength of dispersion force can be estimated from its polarizability. Polar. No? Polarizability is the charge. No? Polarizability is the measure of how susceptible molecules' electron density is to perturbation by external electrical field. So its electrical field, now what will happen is, will it have a more electron density or less electron density? No? That will serve as the instigation in the strength of dispersion force. No? So the more large molecules, they are more polarizable than smaller molecules. Therefore, this will experience stronger dispersion force. So, mas magkadako ang molecules, mas dako pod ang iyang polarizability. Ang electron density niya magkadako. No? So, in dipole-dipole forces, di ba ingon ko sa inyo, it is attractive and repulsive forces at the same time. No? So, what will happen here? The charge of the poles of dipole is seldom more than the fraction of the charge of electron. So, making this force weaker than chemical bonds. No? So, these are the different explanation why dipole-dipole forces is weaker. Another thing is molecules with large dipole have stronger dipole-dipole force. The more stronger ang dipole force, the more it will be weak. So dipole-dipole force are typically stronger than dispersion force. Okay? So here, this is the dipole-dipole force. Mas strong ang dipole compared sa dispersion force. The next one is the hydrogen bonding. What is hydrogen bonding? No? This is under dipole-dipole force. Pero This kind of a bond is stronger compared with dipole-dipole force. Why? No? Because hydrogen, no? In hydrogen bonds, they contain hydrogen. That is why hydrogen bond. No? They contain hydrogen, and this hydrogen will covalently bond to high electronegative elements. What are these examples of high electronegative elements? The fluorine, oxygen, and nitrogen. Nato yun siya mo bond. So kung naga yung fluorine, oxygen, nitrogen, there will be a possibility of hydrogen bonding. So the strong dipole created in this type of covalent bonds creates a strong dipole-dipole interaction with similar bonds. So IMF are weak compared to average covalent bond. Hindi mo na ninyo ha? The large number of IMF force makes IMF forces key factor in determining the bulk properties of materials. So these are examples. Okay, that ends the chapter and lecture about molecules and materials. Thank you for listening, and after this, I will upload this. Then after that, you're going to, we'll have a quiz again for this. Thank you and a pleasant afternoon.